good afternoon, ladies and gentlemen. So, I am very grateful to the previous speaker, Lucy, for setting the scene of what the chemistry looks like in diffuse clouds, because that's essentially where I will pick up and try to build larger molecules and then really going from this diffuse phase into the dense cores and towards making protostars with disks around them, and then making the connection to comets and try to build up chemical complexity across all these various physical stages. So imagine we spent a lot of time in the prestellar core, so if anything, very appropriate. But so, back to the motivation as to why we want to study complex organic molecules and why do we care about the earlier phases of evolution, and why don't we just look at comets and how the material was delivered to Earth? So the reason is, what I will try to demonstrate to you during my talk, is the fact that some of the seeds to life are already actually implanted in these much earlier phases into the building blocks that go on to make comets and eventually planets. So I think this conference is great in talking about this, because we really are covering this full multitude of different environments. So starting from these prestellar cores and dealing with questions as to how physically and chemically these regions look like, and how do we make sun-like low-mass stars, how do we make Earth-like rocky planets, and then how do we actually make from simple molecules the most complex and probiotically significant species. So all of this was already very nicely introduced, so I will not spend much more time here and try to zoom in into where we're actually making these building blocks for comets and planets. And those are the midplanes of protoplanetary disks. So the midplanes of protoplanetary disks are built up from the collapsing material of these prestellar dense cores. In the very deepest layers, you have the highest density. This is where you're hiding most of your material. So this is where you will set the dominant portion of your both dusty refractory material as well as the volatile material, likely in the solid icy form, because it's very cold in the midplane of protoplanetary disks. So I'd like to also point out that by complex organic molecules, I mean the astrochemical definition, in the sense that it's carbon-containing and is only larger than 6 atoms. So to some of you, that might be very simple still. So what we want to know is, can we actually make these complex species, and can we actually implant them into these cometary bodies, and do they actually even make it to the disk? So what do we start with, and what do we get in the disk midplane? So what we start with in these prestellar dense cores are some initially very simple ices. So as your interstellar medium is evolving from diffuse to dense, you will go into areas of higher density, which are colder, and you will start freezing out some of your gaseous molecules, and you will start forming your first ices. So initially what we think will be your water molecule freezing out around 100 Kelvin, and as you enter denser, colder regions, you will then freeze out things like CO around 20 Kelvin. From this CO, under very cold 10 Kelvin conditions, you can kick off some of the earliest chemical processes and then form, for example, methanol on top of this. So in that sense, what we think is the initial icy interstellar or prestellar ices is this first layer of polar water-rich ice, followed by this layer of CO and likely mixed in with some methanol. So if you look at the statistics towards low-mass protostars, what we find is that your dominant ice is water, then 30% is CO2, 20% is CO. And the way that we actually get these statistics is by looking at these ices in absorption against a background source. It's essentially the only way you can try to probe what is hidden in these icy mantles. So these would be the infrared absorption observations. However, the story is more complicated, and observations have shown that even in these earliest phases, you do find complex organics as well, and not just the simple water, CO, and CO2. So just as an example of L1689, over here we're seeing some dimethyl ether lines. And I think Sergio will speak about the different mechanisms that there may be in generating such complex molecules, even already at these extremely simple in terms of chemistry conditions that's still really cold and really dark, so shielded from UV photons. But so it seems that some of these complex organics, maybe at low abundances, are already made in the prestellar phase. And after this, once you start collapsing and you form your central protostar and the disk around it, you really kick up the gears of chemistry by elevated temperatures and also enhanced UV radiation from your central source. And essentially here you're really coupling this physical evolution jointly with the chemical evolution of this infalling material, which is then also starting to build up your protoplanetary disk composition. So in my talk, I will focus on two test samples. So first, I will consider an extrasolar analog, which is IRS 16293-2422, which is located in the L1689 region in the row of Fucus cloud, which we believe is approximate distance 120 parsec. It is a low mass binary with a joint luminosity of 21 solar luminosities, and the binary has a separation of around 600 AU. So if you zoom in into L1689, then you will find the source in this filament 3 area. I am a member of the PILS team. So PILS was introduced by Pierre Cox on the very first day, and it stands for the ALMA Protostellar Interferometric Line Survey. And the survey is special in the sense that it has a very high angular resolution, so we're resolving the slow mass binary with a spatial resolution of around 60 AU, and it also has an excellent spectral resolution of 0.2 kilometer per second, and an excellent sensitivity of 4 to 5 millijansky per beam kilometer per second. That means that if we look at the source, we're really capable of resolving all the individual lines from the molecules, so we're spectrally resolving them. And thanks to the good sensitivity, we can also pick up some of the weakest lines. So over here is just an example towards one single spatial position towards the source, and this is the immense number of lines that we have. So you can imagine that there are a lot of various molecules and many of their isotopologues hidden in here. So it is a very rich data set. So some of the results that have been released by the team so far is the detection of an array of complex organic molecules. So over here, we're hiding the name glycolaldehyde. Then we have ethylene glycol, acetic acid, methyl formate. So over here you see our binary, source A, source B, 600 AU in between. And over here in these 4 panels we see the same molecules, but then zoomed in on source B. So most of the further analysis I will present will be towards this position over here, which is approximately 1 beam, so 60 AU away from the continuum peak position B. And the reason for that is then we're avoiding the optical thickness, which we find on source, yet still maximizing the emission from the rarest species. So what you can immediately see from here that there is already chemical differentiation between the two sources in terms of the spatial distribution of the emission. And in fact, we're also finding that the two sources have different chemical composition, and some molecules have a higher abundance towards B or A, depending on the species. So just some highlights for the things that have been detected. So this isomer group, glycolaldehyde, methyl formate, acetic acid, have been detected. Step up from our simplest sugar, glycolaldehyde, ethylene glycol has also been detected. We're finding 3-carbon species, such as propanal. We're finding nitrogen-bearing species, so formamide, methyl isocyanate. We're finding the full cyanide chain of methyl cyanide, ethyl cyanide, and vinyl cyanide. We're also finding sulfur-bearing species, including sulfur-bearing complex species, such as methyl mercaptan. And as I mentioned, many of the lines that you see in the spectrum are actually originating from the isotopologues of all of these complex organics. So for the first time, we can now actually try to pinpoint the chemical process by which these guys are forming by looking at, for example, the D/H or the 12/13 carbon ratio. Because if we think that some of these species form earlier on, maybe already in this prestellar stage, then we would expect the D/H ratio for those molecules to be higher, whilst for molecules that form somewhat later, when temperatures are warmer, D/H is lower, then those species will also have a lower D/H ratio. So we're trying to now piece together and group these complex organics in order to pinpoint when and where they're being formed. So I would like to also spend some time on sulfur-bearing species. So sulfur-bearing species are interesting in the sense that if you look at diffuse clouds, you get a certain abundance for atomic sulfur. If you now go to dense cores and try to account for all the reservoirs of sulfur, we're missing several orders of magnitude, so it seems that sulfur is a bit of a mystery atom, and there's a deficiency of it in prestellar cores. So sulfur-bearing species could be interesting in trying to understand how the evolution of atoms goes in separating between volatile and refractory components. So what we find towards IRAS 16293 is SO, SO2, CS, H2CS, H2S, and as I already mentioned, CH3SH as well. And here, just as an example, you again see source A, source B in 34 SO2. So we again have all the isotopologues of all these sulfur-bearing species. So both sources are rich in sulfur-bearing species and also show complexity in sulfur. And in fact, source A seems to be somewhat brighter. However, source A is quite hard to analyze because the orientation of its disk is such that the emission lines are much broader. And so in fact, it's much easier to focus towards source B, where the disk is face on, and it's easier to identify the various emitting species. So to summarize what we see around source B, and also in comparison to earlier single dish observations and this interferometric ALMA data set, what we see is that SO and SO2 on large scales stem from these outflow areas and also these wall areas, whilst OCS, H2S, and H2CS are found also on large scales, but mostly in the envelope and not so much near the outflow cavities. All of these are still, however, present in the ALMA data, which means that they're also really present on the small disk scales. So they're found across various scales around this protostar B. Based on the data that we have, we can also derive D/H ratio, specifically in terms of H2CS. So we can estimate the D/H at around 5%, which means that it is highly singly deuterated in comparison, because this implies a deuteration level of 5%. However, if we look at the D/H as we see in other complex organic species, then it's actually comparable and is on that range. So it's not very, very high. It's okay for the source. If we compare this thioformaldehyde with its oxygen-bearing analog formaldehyde, then we're actually finding that it has a higher level of deuteration, singly for sure, and from the upper limits on D2CS as well. So it can suggest that perhaps thioformaldehyde is less processed than formaldehyde, or perhaps it formed under even conditions that were even richer in deuterium. So I will not need to spend much time on 67P, because what we'd like to do is to compare this solar analog Iris 16293 with our own solar system to see whether these two low-mass systems are comparable. So thank you very much to the previous speakers to already explaining everything here. So I will just point out that for 67P, we're really seeing complexity on a whole other level, and we cannot recover this level of complexity towards Iris 16293. It also seems that the comet is rich in sulfur-bearing species and is actually richer in sulfur-bearing species than the nitrogen-bearing species, so giving this extra motivation to be interested in the sulfur bearings. In total, the organics seem to be few percent relative to water, so this is similar to protostars. But stay tuned for some more quantitative comparison in the next few months. CH3Cl has also been compared between the two sources and has already been mentioned by Pierre. So the main takeaway is that there seems to be indeed overlap between the Comet and Iris 16293b, that the ratios relative to methanol are on the same order of magnitude. If we look at the sulfur bearings again, and we compare what we have, then we have overlap in terms of the species detected, so between source B and the comet. However, we're finding much more OCS than H2S for Iris 16293. And however, for example, if you look at the SO over SO2 ratios, they do agree well. So how do we piece all of this together? So the explanation that I think explains at least the similarities and difference for sulfur-bearing species can be summarized in this figure. So it can be that stronger V radiation for the case of Iris 16293 could help change H2S ice into OCS ice, so this is a grain surface chemical process, and to also form some more sulfur-bearing complex species. However, this can also jointly go with a warmer birth cloud, because that will reduce the amount of CO, change the amount of OCS available, which has also been supported by some modeling work on O2. But all in all, the main takeaway is that the physics of formation set the chemical provenances. So then I will jump to my conclusion slide. One back, yes. So I think I was trying to convince you that there's at least partial prestellar origin for the content of our own protosolar nebula. I've also hopefully convinced you that other low-mass systems can be analogous to our own solar system, and this collapse in chemistry en route is very important. So the seeds to life are available on comets, but the roots are already implanted in the prestellar phase. Thank you very much for your attention.